Okay, so I titled this EDA 101. So we're in the EDA industry. That's at least the sort of words that come to mind as the sort of, if you can only say one thing about what Cadence does, it's we're in EDA, which stands for electronic design automation, which of course is software for designers to use. But we also have an IP business as well. And IP stands for intellectual property, which is confusing to anybody outside the industry because that usually means patents. Of course, we have patents as well, but they're just pieces of silicon, often programmable, the tensilica cores. But they're pieces of silicon that you can use in design that are sort of pre-designed. I'll say a bit more about that later. So there are two main parts to EDA. IC EDA, IC stands for integrated circuit, but there's also PCB EDA. So let's look at the IC EDA. And so inside is really where, so it looks pretty boring on the outside, right? A piece of black plastic. Inside, it's pretty complicated. Each of those sort of little rectangular areas you can see that looks like it's repeated really are repeated. Each one of those is a core. And this is, I think, about 6 billion transistors. So it'll give you some idea of the complexity of these things. So Moore's law. So I put this up here partially as a joke because I think it's a great photo, but also to show you that this sort of notion of getting more and more stuff in less and less space for less and less money has been going on for a long time. In fact, before the invention of the integrated circuit, perhaps before, well, by the time you get to the right, I think those are transistors, but over at the left, those are obviously vacuum tubes. And you've probably seen charts like this. This is an old Intel microprocessor roadmap showing where all of their processors fell. It only goes up to 2010, so it only goes up to 1 billion transistors, which today doesn't really get you any kudos. So only 1 billion, not 10 billion. But Moore's law is actually exponential, right? If you look back at that previous chart, it's a straight line, but it's a straight line because it's on a logarithmic chart. And what Moore's law really looks like is this. This is from the Computer History Museum. So basically, things go along, and by the time you get to here, we're up to 240 million transistors in 2006, then up to close to NVIDIA's up at 691, and today we're way off, sort of up on the 5th floor of the building or something at like 10 billion as the sort of maximum. So it really is, pretty much vertical by today. And that reflects in transistor density. So this goes from 40 nanometer to 10 nanometer. And at 10 nanometer, this is a sort of Intel number, 7 nanometer. TSMC calls this essentially the same process. We're at 100 million transistors per square millimeter. So if you think of a period on a printed document, that's probably like a quarter of a square millimeter. So you can fit your 25 million transistors under a period. But to my mind, what's perhaps more interesting, Moore's law says that the number of transistors on a chip doubles every couple of years. But more interestingly, what drove semiconductor for the last 2 or 3 decades has been that the cost of implementing given functionality halves every couple of years. And that means it drops by a factor of 30 in 10 years and a factor of 1,000 in 20 years. And so what that kind of means is that $1 million price tag drops to a couple of $100. And you see that if you look at something like a flight simulator. It used to cost maybe $10 million in the 80s. Now you can buy an Xbox for a few $100s, and it has better graphics than that. And in fact, you can just run it on your iPad or even on your phone. And so a flight simulator that used to cost $20 million now has better graphics on a $500 iPad. And of course, the iPad costs, a few $100. So, but Moore's law is slowing, so that's impacting the semiconductor industry and thus indirectly impacting the EDA industry in general and Cadence in particular. So the new normal is more like this, right? The iPhone 7 was, $500, and depending on how much memory you had on it. The iPhone XS is, $1,000. Again, you can go more if you get more memory on it. There's a lot more transistors on the one on the right. It runs a lot faster. The battery lasts longer and various things like that. But it isn't cheaper. You're not going to see the same thing as happened with, say, calculators, where in the 70s, an electronic calculator was something that was expensive. And by the mid-90s, they were credit card-sized things that people would give away at trade shows because they only cost a couple of bucks to go buy them in quantity. You're not going to see iPhones suddenly drop to be $20. You'll see cell phones of some kind, but with a lot less power at lower price points. But we're not getting that same kind of 1,000-fold reduction over the next 20 years, or at least not based on what we know today about semiconductor technology. So how do you build one of these things? Well, you build them in a semiconductor process. So each couple of years, a new process is released by the companies that build the chips. And they're measured they used to be measured in microns. And so when I started in this industry, we were at 3 micron. And those were the lengths of the transistor when you drew them actually on the silicon. Now because we got below 1 micron, way below 1 micron, they're now measured in nanometers, which are millions, 1,000 billionths of a meter. And the sort of current flow, 28 nanometer that went to 16, there was actually a 20 nanometer short-lived node in there, and then to 7, and again there was a short-lived 10 nanometer node in there. And then in the future, the expectations are 5 nanometer TSMC will be doing risk production later this year, volume production probably next year, and then sort of 3, and nobody quite knows what they'll call it after that, 2 or 1 or 1.5. So we don't actually build one chip at a time. We build them on wafers, and they're either 200 millimeters, which is 8 inches, or 300 millimeters, which is 12 inches. So here's a real wafer. It actually looks like a dinner plate. It's silicon. It's quite thin. This is Tom Kwan at TSMC's sort of awarded wafer for 20 nanometers. So this is a 12-inch, 20 nanometer wafer. I'm kind of assuming, just guessing, that every single die on here is no good and the wafer got misprocessed. And then they cleaned it up after test to remove all of the black dots that the tester puts on to show that that die is no good. And there's an expectation that's not happening anytime soon, but I've got a neat photograph of me holding one, of 450, which is huge. Right? That's an 18-inch wafer. But the equipment for building it is so expensive that, and the volume required for a fab to use those wafers are such that nobody expects them to happen anytime soon. And it requires the whole industry to move. It's no good just one equipment manufacturer building 450 millimeter equipment if you don't also have blank wafers and you don't also have testers and everything that can handle it. So the move from 8-inch to 12-inch was pretty traumatic. So these things are built in fabs. They look like this. This is Intel's fab up in Oregon. They're big buildings. And inside, they look like this. This is an alleyway. Down on either side is the manufacturing equipment. And one thing you'll notice in this picture, no people. It's essentially completely automated. The people that are running the equipment are outside of the fab. The fab is incredibly clean by semiconductor standards, and operating theater in a hospital is absolutely filthy. Nowadays, they don't worry quite so much about keeping the whole air in the fab clean because the equipment is all enclosed. But it used to be that you had laminar flow that have holes in the ceiling and holes in the floor, and the air would basically go down at a relatively slow rate like that, which means the air in the fab's changed every 6 seconds, and then it's recirculated through filters to keep, and that's how you keep it clean. You don't keep it clean by never generating any dirt. You keep it clean by recirculating the air and taking all the dirt out. So a modern fab, just to give you an idea, costs around $10 billion. Nobody quite knows, and it depends a bit on how big you build it and things. But to be economical, you really have to build a fab that's a capacity of about 50,000 wafer starts a month. That's how you measure the size of a fab. So that's 12-inch wafers. And that really means that one wafer starts, roughly speaking, one wafer starts every minute. That, if you multiply up the numbers, that gets you to somewhere around 50,000 when you get to a month. From a financial point of view, that depreciates at about $100 a second. So if you own a fab, you've got something that's you're spending $100 a second on, and so it needs about $500 per second of revenue, maybe more, to justify even owning one. And the result of that is that most people couldn't afford to own a fab, because even somebody as big as AMD doesn't have enough capacity to fill an entire fab. Way back like 15 years ago, Jerry Sanders, who was CEO of AMD at the time, had this catchphrase, "Real men have fabs." And what he meant was that you have to generate, you have to work closely with manufacturing to design real state-of-the-art leading-edge things like microprocessors. Interestingly and kind of amusingly, AMD was the first company to get rid of their fabs. They sold them off to Abu Dhabi's investment arm to create global foundries. And they were then the first major semiconductor company with Lisa Su to have a female CEO. So, you know, real women don't have fabs. So today there are just three leading edge, like on the really leading edge, non-memory manufacturers, who are Intel, TSMC, and Samsung. Global Foundries was on that list. 6 months ago I'd have said 4, but they dropped out and decided not to do 7 nanometer, not to do EUV, which is one of the lithography technology needed for 7 nanometer and beyond, and they're focusing on other areas. In DRAM and flash, there are a limited number of manufacturers too, and everybody else is either fabless, like Qualcomm, say, or Broadcom, or NVIDIA. They don't have any fabs at all, or like people who were in the semiconductor business a long time ago, they're what's called fab light. So Texas Instruments has fabs for the old processes, but for anything leading edge, they never built a fab because it's too expensive, and they wouldn't be able to fill it. So everybody who used to have their own fabs has kind of dropped out, with the exception of Intel and Samsung. TSMC is a pure play foundry. Samsung, in addition to being a foundry, also builds a lot of their own chips for their own businesses. Like if you buy a Samsung smartphone, it's full of Samsung chips. I even wrote a book about it, here, to prove it, called Fabless, The Transformation of the Semiconductor Industry. If you send me an email after this, I'll send you a PDF of the book. You can also get it off SemiWiki. I was working for SemiWiki. Dan Nenny and I put it together. There's actually a piece by Richard Goering, my predecessor, wrote the Cadence sort of bit. Each chapter is about an era of the industry, and then at the end there are, in their own words, where we get a couple of companies who are significant to write about them. So design. How do we do design? And Cadence. So chip design is not really like other design. One thing to sort of compare it with is designing a plane. So it's like designing the Airbus 380. That's the biggest plane, and well, I know it's the biggest plane in the world, biggest passenger jet anyway. But you only have 12 months to do it instead of, I don't know how long they took, 6 years or something. And you're using manufacturing technology that's never been seen before. And you've got to use tools that have never been released. They've just been released and never been used on a real design. And basically, once you get the first one put together, you're going to fly it with passengers. And then you have to start work on the next one, because Moore's law means that you're going to have to build an even bigger plane next year. And you have a year to do it, and you have to use different tools. So here's a very simplified flow of how design gets done. And if you're in engineering, you can put your hands over your eyes and pretend that this is totally unrealistic, which it is. So you have an idea, and in general what you do is you write down the idea in a way that we can actually manipulate it and build a chip from it, and there's a language used for that called SystemVerilog. And we do functional verification on the SystemVerilog, which is using programs called simulation, or perhaps hardware, special hardware for emulation, to check that the SystemVerilog actually does what we want our idea to do. Let's say we're designing a cell phone, then we want to check that when we try and make a phone call that it seems to work, or so on. We then use a process called synthesis to take the SystemVerilog and turn that into a netlist. And the netlist, when I talked earlier about IP, One form of IP are what are called standard cells. They're little tiny building blocks of silicon, and a net list is basically all of those, a lot of those building blocks, perhaps a billion of them linked up together. Now, typically you don't design the whole chip in one go. You split it up into blocks, and partially to divide it, partially because the tools can't handle the whole chip in one go, and partially because you want different people to work on different things. And if you just have everybody working on all of the chip all of the time, that's kind of like getting 100 people to try and write a book with one copy of Microsoft Word. We then go through a process called physical design that turns it into layout. So what actually will go on the wafer, what's on that wafer I showed you earlier, is little polygons, and little meaning 20 nanometers across polygons. And there are a lot of them. And sign-off, which is another part of the checking process that ensures that what we put on the silicon is going to work. And that layout is usually called GDS2. There's a physical verification stage that checks that the layout does all of the things that it should do, and that it doesn't violate the rules that the TSMC or whoever is going to, Intel, Samsung, whoever's going to manufacture it, make sure that it's in line with the rules that they set. And then when you are ready, you do tape out, and in the olden days, you literally did write a tape, and then you'd send the tape off to the foundry to manufacture it, or send it off to the mask maker to make masks. So IP, I talked about. I'm not talking a lot about IP, but IP kind of fits in two places. I said IP are little structures that go on the silicon, but there's another form of IP which is really in SystemVerilog level, where it goes through synthesis as well. And that has the advantage that it's independent of what you're going to use to manufacture it. It doesn't depend directly on what library you're using, and it doesn't depend on what manufacturing plant is going to build it. Whereas typically the lower line there that goes straight into physical design usually has to be altered for every manufacturing process to fit their design rules. As I said, chip design is not really like other design. The physics is constantly changing, which means you're sort of building with untested stuff. You've got a very short design cycle, and it's very unforgiving because it's often driven by consumers. If you're going to ship an iPhone, if you're Apple and you want to ship the next iPhone and you want to meet the Christmas market, it doesn't do any good to deliver it in January the 15th. And if you want to meet the Chinese New Year, it's not going to do too well to, oh, we're a month late, it's end of March. So the design costs are huge. They didn't used to be quite so huge. This is some IBS numbers. So in 65 nanometer, it costs you only $28 million to design a chip. But by 5 nanometer here, the estimates are $500 million. Now you'll notice there's quite a big purple bar there. That's all software. So in some sense, that's not the IC design. But that's all part and parcel of getting a system out. If you're going to get a chip out for autonomous driving, a huge portion of that is going to be the software. So this was Lisa Su, the real woman who doesn't have a fab, giving a keynote at CES that I was at just a few weeks ago. She announced this Radeon, I think they call it 7, it's Roman numerals. It's 19 billion transistors. And I just divided that number by the number of days in 2 years. That's 25 million transistors a day, the rate that they had to design that at. Now, of course, that's not one person doing that, but even so, that's an incredible amount. When I started in this business, a chip was 10,000 gates, so maybe 40,000 transistors. That was the state of the art. And if we got 1,000 transistors a day design, that would be extraordinary, right? So. But unlike the plane that doesn't have to fly the first time you put it together, because you sort of do a lot of testing and maybe you make some adjustments and so forth, and it has to fly eventually, of course, otherwise you're not going to get any money back by selling them. But chips are kind of expected to work first time. And as a result, the bulk of the tool investment is kind of risk management. You're making sure that the plane is going to fly. You're making sure that the chip is going to work. And unlike software, where you can compile it and run it and see whether it works or not, the equivalent is to tape out the chip and build it. That takes multi-millions of dollars just to build a chip, even if you only want one, which is known as a prototype. And it takes literally months to get the prototype back. So that's not the way you decide whether your design is good or not. And the result is that the verification, I talked about verification of the SystemVerilog and then verification of the layout, the physical design, Pegasus, is about 3/4 of the design cost. Most of the cost goes into making sure that the chip's going to work, not into actually building the chip. And you don't really have the opportunity of not optimizing the chip to make, backing everything off to make your life easy for yourself, because then it's like, well, why build a $10 billion fab if you're going to build something that you could have built in the previous fab? Now, the people that we sell to sell into end markets. And so let's see what the end markets are. I like to say that the world changed on January the 9th, 2007. So that's like 12 years ago now, when this Starbucks barista, Hannah Jang, took a strange phone call, which was for 2,000 lattes to go. You'll know what this is if you've ever seen the video of this, which you should go and watch because it's worth watching. And of course, that was Steve Jobs making the first phone call on an iPhone from the stage in Yerba Buena Center for the Arts where the iPhone was announced. And that's kind of the beginning of the smartphone era. And smartphones are huge. It's like there are 1.5 billion smartphones shipped in a year. No semiconductor market is anything like that big. There's a lot of silicon in each one, but even if there wasn't, there's 1.5 billion chips. So when Apple builds an AX, it's shipping 300 million phones a year or whatever their number is now. So they basically fill a complete fab at TSMC in order to do that. You can see here how, on the green bars, how the market has grown. The last bar is only for 3/4, so it hasn't actually fallen off a cliff. It'll basically be flat, but I couldn't find a graph that had the Q4 numbers in. They may not have been released yet. The next biggest, or the next biggest industry, or the most interesting industry, because it's growing fast, is automotive. And there's two markets there. The old automotive, which are kind of old. They were built in old processors that have been around for 10 years, mostly analog, 8-bit microcontrollers. It's all about reliability and price. New automotive is things for basically self-driving cars, and that requires modern processes, but it still requires automotive reliability. And just as a number, there's about 100 million vehicles a year. So it's, in terms, compared with the phone industry, which is 1.5 billion, it's only a 15th the size, but there's a fair bit of silicon forecast to go into cars, and this shows the percentage of the car cost going into electronics, and it's predicted by 2030 to be half the cost of the car will be electronics, and some of that is, it's not all semiconductor. There's other things in there. So, and of course that's the semiconductor revenue. As a rule, our revenue in the EDA industry is a percentage of the R&D budget of the semiconductor companies. High performance computing is the third of the sort of four big markets that everybody focuses on. So that's driven by cloud data centers, people like Amazon's AWS. Increasingly, a lot of the silicon is going into deep learning training. This picture is Google's TPU, the third version of Google's TPU. But NVIDIA, for the moment, is kind of winning that. If you go to AWS or any of the other cloud people, you can get a server with an NVIDIA processor on, and you can use the GPU to do training of your neural nets. And then IoT. And just as obviously at some level, a car and a phone is a thing, but they're their own markets, so we don't count them as things. It's extremely fragmented. The focus today seems to be on industrial IoT, things like predictive maintenance, because the return on investment is clear there. Consumer IoT, it's much harder to make money because the chips are selling for 50 cents or $1, and they're a thermostat or something. And but and it's a Nest thermostat's not the same as somebody else's thermostat, and it's a different chip that goes in your smart security system and so on. One particular area of interest is voice, Alexa and things like that. It's not quite clear how significant that's going to be. Voice is, Alexa's in a lot of homes, but people don't use it for anything terribly significant. If you took it away again, it's probably not going to be the end of the world, whereas if you took people's mobile phone away, they're going to complain a lot more.